All right, so welcome to our first video. So calculus 1, so we begin with the study of limits. Now, if you've had any exposure to calculus before, I know that for many of you, you want to jump to the recipes for derivatives. But let's slow down for a second, right? Because the idea is every derivative, if again, this is assuming, let's say you took calculus in high school, but every derivative comes from this idea of a limit. So let's start with limits. Now, notice I'm giving you a function, right? So x cubed minus 1 over x minus 1, and I even have the graph of the function here. Now, a pre-calculus type question would be something to the nature of, okay, if I give you an x value, say, let's say we let x equal 2. Then what is the y value? Well, this, again, very easy, very pre-calculus. So here's when x is equal to 2. And if we follow that all the way up, we could figure out what y is equal to when x is equal to 2. Now, but what if, and notice that the graph is perfect. We could find any of the y values that we would like. But there's one y value that's restricted from us, right? Notice what happens if we allow x to equal 1, right? F of 1, in other words. Well, let's start with if you plug in 1 for x. Notice that you would, immediately you can notice that you would be dividing by 0, right? If you let 1 minus 1 be in your denominator, then we know automatically we're dividing by 0. It's also true that our numerator is 0, so we have 0 over 0. But that is one x value that is restricted from us. We don't have enough access. So what I'm going to do is I'm going to draw, try that again. I'm going to just draw an open circle here. So we have this hole in the graph, this hole that, this is the only value that is restricted from us. But what if we're interested in that? What happens when x is equal to 1? Well, clearly, analytically, we cannot just plug 1 in for x, right? We cannot divide by 0. Speaking of which, if no one has ever shown you why, like if somebody were to walk up to you and say, why can't you divide by 0? What would you say to this individual? Well, let me see if no one has ever explained to you why you cannot divide by 0, please let me be the first, right? Because it's a shame to just think of it as another rule and then we must follow. So to a mathematician, if you would like to divide by 0, so let's say 2 divided by 0. To a mathematician worth their salt, they would say, okay, well, if you'd like to divide by 0, you may, but you will have to suffer the consequences. Well, what would the consequences be? Well, let's take the following little equation. Say x is equal to 2 divided by 0. Now, if you were to multiply both sides of this equation by that denominator, we would end up with something like 0 multiplied by x is now equal to 2. And of course, if we accept that anything multiplied by 0 is 0, then we end up with a statement 0 is equal to 2. Now, again, to a mathematician, if you are willing to accept that there is no difference between the number 0 and the number 2, right? That the law of identity is not something that you are interested in keeping, then to the mathematician we'll say, okay, well, feel free, proceed to divide by 0. But if you would like to keep laws of identity, right? If you would like to continue stating that 0 is different than 2, then, well, we are forced to not allow division by 0, right? So it's all about what axioms would you like to keep. If you'd like to keep the law of identity, then you cannot have division by 0. Hope that makes sense? Now, the question still remains. You and I are interested in what happens when x is equal to 1. I can't plug it in because I end up with a nonsensical statement, 0 divided by 0. So then, but what if we just choose some numbers really close to 1? Right? I mean, let's say 1 is $1. So $1.10 is pretty close to $1, or 90 cents is pretty close to $1. In fact, we can get even closer, right? We could say 1.01, $1.01, is even closer to 1 than $1.10. And of course, 99 cents is closer to 1 than 90 cents. In fact, we could continue to play this game. So now let me pose the question. Let's take 0.9. Are there any restrictions with plugging 0.9 into this function? Well, no. I mean, we can't plug in 1, but we can plug in anything else, correct? So assuming my math is correct, assuming I'm going to plug 0.9 in, you should get back out 2.71. All right, well, what if we plugged in $1.10? So we should get back out 3.31. Again, if you see any silly mistakes, run with it, okay? So let's do better. We can get closer to 1. So let's plug 0.99 in for x. Now, 0.99 gives us 2.97, okay? And if you plug in 1.01, you should get 3.03. Now, my question to you is, what if we kept playing this game? What if we kept picking numbers closer and closer and closer to 1 and then plugging them in? What do you think, or what would your prediction be for the value of when x is actually equal to 1? Well, you could go a little bit farther. You could try plugging in 0.999. You could try plugging in 1.001. And you would see that it appears that as x gets close to 1, right? See these arrows? This is x getting closer and closer to 1. It appears that y, now the y values are the values on the graph. It appears that your y values are getting closer and closer to what number? Well, it looks like they're getting closer to 3. In fact, we could make a statement. Now, can we make the statement? This is a question. Can we make the statement that f of 1 is equal to 3? No. No, you absolutely cannot make that statement. So what type of statement can we make? Well, here is the type of statement that we're going to make. We're going to say the limit of f of x as x approaches 1 is 3. Notice the difference between these two statements. F of 1 equals 3 it does not work. You can't plug 1 in. But we can define that approaching 1 as what we mean when we say a limit. So the limit of f of x as x approaches 1 is 3. So let me try to give an informal definition of a limit. So, and I know that this can be a mouthful, right? But just bear with me here. So if f of x, that means your y value, if f of x becomes arbitrarily close to a single number L, that graph is getting closer and closer to 3. Y is getting closer to 3. As x approaches some, we call it some x value we'll call c. So as x approaches c. Let's translate that. So x in this case was approaching 1. So the c value would be 1. And as x approached 1, y is approaching 3, right? That's what we're saying. So if f of x becomes arbitrarily close to a single number L as x approaches c, then, here it is, then the limit of f of x as x approaches c is L. So we are defining our answer to be 3, okay? Now, how do you find limits? Well, I've just given you this is one way that you can find limits. You could do a table, and you just keep picking values that are closer and closer to the number that you're interested in, okay? You could do one more in this fashion. So this is just a numerical approach to finding limits. So notice the example says, evaluate the function of x over the square root of x plus 1 minus 1, and at several x values near 0. So meaning the limit, as we're thinking about the limit as x approaches 0. Well, I'm not going to fill out this table for you, but the idea is if you wanted to pick some numbers that were close to 0, right? You could pick, for example, 0.01 or 0.0001, and you could continue picking numbers that are closer and closer to 0. But here's the main thing, and if you could, and I know it's easy to get distracted, right? You maybe have 3 tabs open and your phone in your hand already, but bear with me. I want you to understand what this term means, as limit as x approaches 0. So here it is. So don't you agree with me that here's where, with this red dot, here's where x is equal to 0, right? If you want to approach 0, you can imagine you're on one side of, right? This is just you, or this is you. Okay, don't get jealous of my artwork. And you want to approach 0, then that would mean that you're walking towards 0, correct? So this is what we mean when x approaches 0. You're picking numbers closer and closer and closer to 0. And what comes back out is, well, what is y doing? Because these are all the y values. All the y values are on this graph, except obviously we have a hole here, right? So if I choose x is -1, then this would be the y value. If I choose x is -1/2, then this would be the y value. Do you see how I'm getting closer and closer and closer and closer to 0, to some number, as x gets closer and closer and closer to 0? Okay. You can try this on your own. Let's see if you could fill in the table if you'd like. But let me go ahead and give you the answer. In this case, the limit as x approaches 0 of that function is equal to 2. Right? You could see that here's where y is equal to 1, and here would be where y is equal to 2. Okay. So that is one way of finding limits. And I don't like this way, right? Because for one, they're nice but what if that were really approaching 2.1 or 2.001? Right? I mean, we would have to choose a whole lot of numbers to be confident in our prediction. If your only way of doing limits was tables. So but that's one way. That's one way you could do limits, is with tables. So let's see what else, other ways we could do limits. So the second way I'm going to show you how you could find limits is by looking at the graph. For me, I don't know about you. For me, I need to see the geometry if you want me to remember what I'm doing. I either need to see it in a word problem, or I need to see the geometry. Otherwise, I either just don't care, or I just don't understand. So let's see if we can understand the question. It says, find the limit of this function as x approaches 2. Okay, so let's translate that. So x is approaching 2, meaning the limit as x approaches 2. Okay, well, let's now look at our function. So this is what we call a piecewise function. And it's fairly intuitive as to why we would call it a piecewise function, because your function has multiple pieces. You would need all the pieces to put together the function. So let's take a look at the first piece. Okay, so the first piece is f of x equals 1. So y always equals 1 if x does not equal 2. Let's see if you and I can draw that. Okay, so y equals 1 when x does not equal 2. All right, well, let's just say that this is 1, okay? And we'll say that, no, we'll do it by tick marks. So we'll say that this is 1, and we'll say this is 2. Okay. So here it is. When x does not equal 2, so all of these values that I'm drawing is when x does not equal 2, right? And notice that when x, so like for example 3 is not 2, so it's saying y equals 1 for every value that is not 2. Okay, well then now let's look at the second piece. So the second piece says if x does equal 2, then y is equal to 0. Okay, so let's now draw that. So here's where x is equal to 2, and we know when x does equal 2, y is equal to 0. So taking all of those, you have a line, a horizontal line with a hole in it, and then you have a solid dot. That is your graph of your function. Now, let's see if we can use that graph to discuss the limit. Okay, so here it is. So as x approaches 2, that means I'm getting closer to 2 from both sides, right? Let's see if we can draw that. So this is x getting closer to 2. So you might start off back there at 3, then you get to 2.5, then to 2.25, and you just keep walking. You're getting closer and closer to 2. But now the real question is, what is y doing as x approaches 2? Well, notice that y is 1 here, y is 1 here, y is 1 here. Y is continuously equal to 1 as you get closer to 2. But what about, and here it is, what is the difference between these two questions? What is f of 2, and what is the limit as x approaches 2? Because these are two different questions. Let's start with the first one, f of 2. Well, here's where, when x is 2, what is y? That's what that question's asking. Well, we know when x is 2, y is equal to 0. But that has no bearing on what the limit is doing. This is the hard part for a lot of students to understand, because a lot of times students want to say the answer is 0. No. The answer is only 0 at 2, not getting close to 2. If you're getting close to 2, then your answer is what? 1. So the limit of f of x as x approaches 2 is 1, even though f of 2 is not 1. That is, I know that can be confusing. You give yourself a little bit of credit, give yourself a little bit of a break, okay? Cut yourself some slack, because, well, it's supposed to be summer, and you guys are overachievers, so you're signed up for calculus. So relax. This will start to click. I promise you, it'll click. It's a whole new language right now. Here's the takeaway. There's a difference between asking what the limit is and asking, so the limit as x approaches 2 is a different question than f of 2, okay? One is a pre-calc question, the other is a calc question. So now, let's see if we can get into some problems, right? So when do limits fail to exist? So let me start. So I'm going to read off here. So there's 3 different ways that limits fail to exist, but I can sum it up for you very quickly, okay? The graph should be approaching the same number from both sides, the same L from both sides, if for the limit to exist. So do you see how we're approaching 1 from this side, we're approaching 1 from this side, we're approaching the same number from both sides? So here is one way limits fail to exist. Let's start there. So if your function approaches different numbers from the right side of C than it approaches from the left side of C. So here's an example. If you were to graph the absolute value of x over x, right? This is what I'm going to do here. This is the graph of the absolute value of x over x. It would look like this. And forgive me, I know that the tick marks say from 0 to 10, but just because I can't zoom in, let's pretend that this is 1, and then let you and I pretend that this is -1, okay? But here's what the graph would look like if you were to graph this on your calculator. To my best, these are not very straight lines. I agree with you. Okay, so this is what the graph of the absolute value of x over x looks like. Now, so notice the question asks, well, what about when the limit as x approaches 0? So will you agree with me that if you approach 0 going this way, you're going towards -1. Whereas if you approach 0 from this direction, you're going to +1. You'll agree with me, right? Then agree with me that it's not approaching the same number from both sides. Right? One is approaching the +1, the other is approaching -1. So it's not approaching the same number from both sides. So in other words, this limit of this function fails to exist. You can just put DNE, does not exist. The reasoning is because it's approaching different L from each side of C. Here's another way of restating the same thing. So if you were to look at the graph of 1 over x squared, okay, it would look, I'll do my best here, look something like this. Okay, so this is the graph of 1 over x squared. And notice that this question says, well, what about the limit as x approaches 0? Well, let's pretend. So if you start approaching 0 from the right of 0, what's your graph doing? Okay, remember, so you're over here, say at 10, and you're walking towards 0. Well, as you get closer and closer and closer to 0, see how your graph is just shooting up to positive infinity? What about if you approach 0 from the left? Well, here's you approaching, getting closer and closer to 0, and then look at what your graph is doing. It's again going up to positive infinity. So there's 2 ways of answering this question. But you're saying the same thing. I would prefer you say that if I were to ask you what is the answer here, just to simply state does not exist, because it's not approaching the same number from both sides. But you could also state this, that the graph is approaching positive infinity. Either way, you're saying the same thing. You're telling me why it does not exist. It does not exist because it's approaching infinity, or it does not exist because it's not approaching the same number from both sides. All right, so I'll read it to you. So if f of x, if your function is increases or decreases without bound, well, that's what we mean. If you're going up to infinity, you're increasing without bound as x approaches c. That would tell you your limit does not exist. Just remember, it has to approach the same number from both sides. The last situation that we run into when limits fail to exist is if your graph is just oscillating back and forth, right? If it's oscillating back and forth between two fixed values as x approaches c. Let me make sure you understand. So in this example, you have the limit as x approaches 0 of sine of 1 over x. And if you follow me down here, this is the graph of sine of 1 over x. And now just look at the graph here, right? I mean, you see how this, if you're getting closer to 0, look how your graph is just oscillating back and forth, up and down, right? I could show you this if you'd like. We could do it this way. I'm going to just choose what I'm doing here is I'm just choosing some values for x that are closer to 0. Right, so we'll start off at 10 cents, that's close to 0. A penny is even closer to 0. 0.001 is even closer to 0. And now, if you take each of these and plug them in to 1 over x, so now it would be 1 divided by 0.001, or 1 divided by 0.01. So if I plug those in, this is what we would get. So if you divide 1 by 0.001, you're going to get 1,000. If you divide 1 by a penny, you're going to get 100. And if you divide 1 by a dime, you're going to get 10. Okay, so let's see how much you remember from your trigonometry. So what is down here, what is the period of your sine curve? Right? Just if you're dealing with regular sine of x, what is the period of sine of x? Well, the period of sine of x is 2 pi. Do you know what that means? That means it takes a length of 2 pi for your sine curve to complete one cycle, right? After it's gone from, say, 0 to 2 pi, then it just starts over again. The graph starts over all over again. What about the range of your sine curve? Right, so just regular y equals sine of x. What is the smallest value you ever get out of sine? Well, the smallest value that you ever get out of sine is -1. And what's the largest value you would ever get out of sine? Well, the largest value is +1. So your sine curve is literally always oscillating between -1 and +1, right? My apologies, that's drawn horribly. But your regular sine curve is always oscillating between -1 and +1. So to kind of make this point clear, let's just do one of these, right? So let's assume as x goes from 10 cents to a penny. So x goes from 0.1 to 0.01. What is the change in x? Well, the change in x, that's fairly easy. So if you if you do 10 cents minus a penny, you would have 0.09, right? So we moved 9 cents closer, or 0.09 closer, when we moved from point to 0, from 0.1 to 0.01. Okay, well, how did y change? So y changed from 10 to 100. So the change in y would be 90, 100 minus 10. So, and now, just to make sure you understand everything that's happening here. So if you take your change in y, which is 90, and you divide that by 2 pi, because 2 pi is how long the period of the sine curve, you would get roughly 15. What does that mean? Here's what it means. So as your x value got closer to zero, your sine curve repeated itself 15 times. In fact, if you were to go do this again, going from x is 0.01 to x is 0.001, that's even closer to 0, your sine curve would repeat itself 150 times during that interval. So all in all, this is just to state that this does not exist because it's not approaching the same number, right? In fact, it's not approaching any number at all. It's your curve is, look at your curve here. Your curve is just bouncing up and down, back and forth between -1 and 1. It's just oscillating. So the limit does not exist. Okay, so we're going to conclude this video. I know this is long. This will be the last bit of material that we're going to do. And what I'm going to do is I'm going to do 23 for you, okay? And then at the beginning of the next video, I'm going to do 24. So between now and then, maybe you should try 24 and see if you and I are on the same page, because this will tell you if you're getting good at this. All right, so we're going to use this graph to answer 23. So let's start. Let's start with part A, f of 1. All right, so listen to me. If you don't see limit, then this is not a calculus question. This is a pre-calculus question. So here it is. When x equals 1, what does y equal? Well, you see your solid dot, right? So when x equals 1, y equals 2. All right, now let's ask the same question. Well, what about when you approach 1? What about as x approaches 1? All right, well, here's what your graph does when you approach 1 from the right side. And here's what your graph does when you approach 1 from the left side. Let me ask you the question. Are you approaching the same number from both sides? No. So the limit does not exist. All right, same type of question. What about f of 4? Well, that's just a pre-calculus question. When you plug in a 4, what do you get out for y? Well, when x is 4, look at the hole in your graph. There's no y value. So f of 4 does not exist. Okay, well, what about, instead of what's happening at 4, what about when you get close to 4? All right, well, here is you approaching 4 from the left side, and here is you approaching 4 from the right side. So as x approaches 4, what is your graph doing? What is your graph approaching? Well, and more importantly, is it approaching the same number? Yeah, right? Like if you were on one side and your friend was on the other side and you started walking, right? Wouldn't you guys meet? Wouldn't you be able to shake hands, right? Right here. So indeed, it's approaching what? It's approaching 2. Okay, so we'll conclude. Thanks for your patience. Next time I see you, I will do 24. Take care.